Okay, welcome everybody. We're going to start now in a minute. Pierre is going to be giving us a presentation with his expertise on the images of the James Webb Space Telescope, and we look forward to this. I'm sure it's a highly interesting topic for everybody, really. If everybody could just mute the mics, and then if you want to ask a question, click on the hand. Okay, and then we respond. Thanks. Go ahead, Pierre. Thanks.
Okay, thanks, Derek. Good evening, everyone. Let me just few corrections. First of all, this is not a presentation. It's a discussion, and it's in response to a request from Elaine. Can I just say, remind everyone that Peter Kotzer is giving a talk on an update on the James Webb Space Telescope to U3A in the Catholic Hall live at 10 o'clock on the 1st of September. Okay, there will be no Zoom link. So I would strongly recommend that all members of the HIC attend that talk live on the 1st of September. Peter, will you send the necessary reminders once you've got Peter's bio and synopsis of what he wants to distribute to U3A?
Hetty, if it's possible.
You'll have to discuss that with Gert Klaassen. I think the U3A, when Derek and Nick and I actually spoke to them, they said they took a conscious decision to not do Zoom meetings unless the guest speaker was addressing them on Zoom. We can ask Gert for a recording if you're not able to attend in person, which I won't be surprised. Okay, in any case, let me carry on with tonight's talk. So it's in response to Elaine's request to discuss the fantastic images.
Honeybud? Hits? Okay.
Right. Now, I think this just gives an overview. I'm sure that Peter will give more detail in his detailed talk of what James Webb actually looks like. I think these images are quite familiar with the thermal shield or sun shield. It's about 5 tennis courts large, so this is not small. And the 18 hexagonal segments of metal beryllium coated with gold. I think Peter will give more technical details. One knows that it's a 6.5 meter mirror, primary mirror, beryllium and gold, but this photo gives an indication of size. One doesn't realize how big 6.5 meters actually is until you compare it to humans standing around it. Now, first of all, just three comments about James Webb. It's very big, 6.5, as we saw in the previous image, versus Hubble's 2.5. Now, as the resolution is inversely proportional to size, the resolution of James Webb is much higher than any other space telescope or any other telescope at the moment. The second thing to bear in mind about James Webb, it's very, very cold. It's permanently fixed at the L2 Lagrange point, 1.5 million kilometers from Earth, and it's shielded from the sun very carefully. So it's very cold, which implies that it can detect very cool stars at longer wavelengths, which can penetrate dust. So the resolution is enormous. And because of the infrared wavelength, because it's operating at such a low temperature, it can penetrate dust and look far further back than any other telescope on Earth yet. Now, first of all, just the objectives, bear this in mind when we look at some of the images or discuss some of the images. It's looking as far back as possible. I think that was one of the first objectives of the whole project, 10 years or 15 years ago. The second important science objective is because it operates in infrared, it can penetrate through or see through dust. So it can compare images of early galaxies with what we're seeing nowadays. It couldn't be seen by Hubble, but you can now see it, Hubble invisible. With the James Webb, you can see it in infrared. Birth of stars and protoplanetary systems. By observing many different stars, you can see, you hopefully can catch them at various stages in their development. And there's at least one image which is quite fantastic, which we can discuss later. And then, of course, because it's got a very sensitive and really state-of-the-art spectrograph, it can look at planetary systems, determine the chemical composition of exoplanets' atmospheres, and look for signs of life. Before we get to the images, let's just have a look at the instrumentation which is used, or the instruments which are used. The instrument module has four main components. The near-infrared camera is the workhorse. Give more detail about that. It's from 0.6 to 5 microns. Just to put it into perspective, I think James Webb is about from 0.35 or 0.3 microns to probably about 0.7 or, well, probably 0.75 or 0.8 microns. So that's in the visible spectrum. So but that is the real workhorse of the, and then which makes it so spectacular is the spectrograph. Also in the near infrared, we'll look at more detail of that, but that is, a combination of these two is extremely powerful. And then that's it longer, from 5 to 28 microns. That gives a different perspective. Exoplanets, we'll look at what they look at now. And then, of course, because of the high sensitivity, the fine guidance sensor is pretty important because it must keep it stationary for long exposures. All this information comes from a website, obviously. I'm just giving a summary, which I think is relevant to the background of the images that can be discussed. 0.6 to 5 microns, I think I've already mentioned that. And here it says that there's visible light, and here's what the nerd cam can look at. That's cooler red stars, and its dust is transparent, so it can look very far back or very deep into galaxies. It's also equipped with coronagraphs, instruments that allow astronomers to take pictures of very faint objects around a central object. So this is the main workhorse of the JWST. Then it's got an infrared, near-infrared spectrograph, which I think is literally a mine, an incredible source of information. It's a very, very fancy spectrograph or some spectrometer, whichever term you want to use. Analyzing the spectrum can tell the object, can tell us its physical properties, temperature, mass, and chemical composition. That's very, very important. Fingerprinting the universe. I think Kees gave a talk on that many, many years ago. It's also very fancy because it can observe up to 100, take spectra of up to 100 objects simultaneously because of what is discussed as this micro shutter technology. It's basically small little shutters, almost like pixels, which are magnetically operated. So the lifetime of the James Webb is 5 years. I think NASA has been consistent in exceeding its design lifetimes. But in any case, when you've only got it up there for 5 years and you can't go and renew it or maintain it, you've got to get as much science from it as possible. And this micro shutter array in almost, well, by 2 orders of magnitude, expands the information that the JWST can obtain. Then it's got the mid-infrared camera and spectrograph. I think the combination of camera and spectrograph is almost natural. In principle, you can bleed off a part of the incoming light and put it through a spectrograph to determine redshift and the spectra and the composition of what you're looking at. So the mid-infrared is from 5 to 28 microns. To see, it sees redshift of distant galaxies, newly forming stars, and faintly visible comets, as well as objects in the Kuiper belt. To give an idea of size, once again, there are lots of humans with the instrument module behind it fully assembled. So it is not a simple instrument at all. Now, I'm just going to show a few images covering the science objectives of the JWST. But before I carry on with this, I think it's important, it's my perspective, that the instrument is so versatile. One of them shows images taken through 4 and in some cases even up to 6 different infrared filters. So you're actually taking small slits at different wavelengths. And when you combine them, it's almost like assigning the different filters to different channels when you want to compose or superimpose pictures to form the final image. So I'm pretty sure that before the first images were actually released, the science team experimented with lots of different combinations and recipes, almost like a Hubble palette, but there are different combinations used. So the first, my interpretation is that you cannot just visually look at the spectacular images. You need actually to read the notes that NASA supplies with each of them to really understand what you're looking at. Now, this, I think, was the very first image released by James Webb about a year ago. The pillars, not the pillars of creation, the Carina Nebula. And there is the discussion of it, the mountains and valleys, landscape of mountains and valleys called the cosmic cliffs. Now, I don't want to read through the whole, but I'm taking this as an example. This gives you the information of what the previous image is actually, how you must interpret it. Right at the bottom here, some information about the object. It's 7,600 light years away, imaged by the near-infrared camera as well as mid-infrared. The NIRCam gives it crisp resolution and unparalleled sensitivity, and it therefore unveils hundreds of previously hidden stars and even numerous background galaxies. And then the mid-infrared view young stars and their dusty planet-forming disks shining through in the mid-infrared, appearing pink and red. It reveals structures that are embedded in the dust and uncovers the stellar sources, massive jets. Let's just go back to the previous one. Now that you've ingested some of this information, let's just go back to the image. You can see the pin shop. It's interesting that these characteristic, all the stars have got the characteristic, I almost want to say, Bartonov mask spikes. I assume, Peter, maybe you can answer this question now or later. I assume they do use something like a Bartonov mask, although electronically to focus it sharply. And that's why one sees these characteristic spikes in all star images. But I think this example illustrates that you can look at the image, you can admire it, but you don't really know what you're looking at until you've read the blurb that attaches the image. Any comments or discussions or some things that you see in these notes at this stage?
I just want to draw your attention to the fact that some of these peaks are actually 7 light years high. And if we take that into perspective, the distance to the closest star to us is 4.5 light years. So that is enormous distances that we are covering here at the moment.
Wow. Yeah, I
Thanks
think
for that.
that image is actually, if you look at the whole Carina Nebula, it's a very small part of it, sort of up towards the top right of it. But it's you know, all the detail is just incredible. And by the way, Pierre, I think that those spikes, that's a natural thing that you sometimes get depending on your lens and stuff. I get those star spikes like that just without, you know, just from images I sometimes take, depending on the combination of camera and focal length and stuff.
Yeah. Pierre, can I just ask? I haven't had a chance to read through all that. I'll have to do that later. But I was also wondering why these stars are always looking like, with the 6, you know, 6, like, was it some kind of diffraction pattern or something? And then the other question was, are you going to kind of go through it and show us now what it all means? Because from what I understand, you're saying that they take different images and then they put it all together, and only then do they get this picture. So they would have all those different cameras and spectrographic analysis and everything, and then there's a whole composition before they get to this image that we see.
No, I think we should, Elaine, or maybe I didn't explain myself very clearly enough. One must distinguish between the image and the spectrum. The image can be taken through the NIRCam or the mid-infrared instrument, and you can actually use lots of different filters on each of those instruments so that you get slices or segments at different parts of the wavelength spectrum. And then you can superimpose all those different slots or slices, as it were, into one optical image, or what we can see. It's got nothing to do with the spectrum. The spectrum is used to determine, well, first of all, the redshift, in other words, the distance to the object, because it measures the spectra, and from the spectra's redshift, you can determine how far away it is, and how fast it's moving towards or away from us. And by also taking spectra, you can determine the composition, the chemical composition of the object that you're looking at. So it's doing 2 processes in parallel. The one is an image, composing or developing an image, and the other one is determining the chemical and other details of the object that you're looking from the spectra. Just by way of example, SALT is essentially a spectrographic instrument. It's not an optical instrument so much, and its main benefits, its main use of its information is from a spectra, which are measured by it. Does that answer your question, Elaine?
Yes, thank you, Pierre.
Okay.
Yeah, it's Chris. I can comment on those spikes. Hold that image. That's perfect to discuss this. So the spikes are indeed diffraction effects. When light meets an edge, then you get a spike at 90 degrees to the plane of that edge. Now, this telescope comprises several mirrors that are hexagonal in shape, and it's the edges of the mirrors that are causing those 6 spikes. So for every edge, you will get two spikes, one in opposite directions. But because it's a regular feature, you have an addition of the spikes from the two sides. So you get the 6 lines. But if you look carefully, you'll see horizontally, there's another pair of spikes sticking out. And those are because of the support structure for the secondary mirror. And that has got 3 legs, and 2 of them align with the hexagon edges of the primary mirror, and the third one doesn't. And it's the third one that's causing that little faint spike in the middle.
Wow, thanks, Chris.
Pierre, can I just maybe comment on the frequencies and the image?
Yes, of course.
Yeah, Pierre. So Elaine, you can also download the JWST data from the MAST website or from the ESA website. So, and then you can actually make your own images from the. So just to bear in mind, the frequencies are, they're in infrared, so it's not visible to the human eye. So what they do is they take a wavelength, and normally the convention is take the shorter ones and allocate blue to that. The longer ones they allocate red to, and the in-between ones goes, the in-between one goes to green. So to make an RGB image, which is totally artificial, but just to give us a picture out of it. So I have done this. I have downloaded the data from JWST. In fact, for the first one that Pierre showed up, I did my own image. I believe I've got a better result than the one that they showed. I've got more detail, finer detail, and some of where they've got dark shadows, I've got some visible sort of image in there. So at some stage, maybe I can just compare that if there's time. But yeah, so I just wanted to mention that anybody can, it's publicly available. Anybody can download this data and play with it. Thanks, Pierre.
Okay, well, all I can say. Oh.
Sorry, go ahead, Lang.
I just wanted to say wow, because it would be fascinating to see how you actually do that.
Well, at some stage we can have another session on that if there's enough interest.
Well, you more or less promised 2 more sessions now, Derek. The one is what Elaine has just asked now, it's the image processing from ESO images that you download and then process. And the other one was actually the using professional telescopes to, which Peter was referring to recently in the astrophotography WhatsApp group. In any case, thanks for that, Derek. Any other questions regarding the Carina Nebula? Then let's move on to the next. This is also one of the first images released by NASA. But this in fact is the deepest field image yet taken ever. And this was, one can understand, that's one of the primary objectives of James Webb, is to actually look as far back as possible in time. And this is the result of that. What is very obvious here is a lot of gravitational lensing. You can see all these images are smeared out almost in a circular form, which implies that there's a huge concentration of mass over here. Sorry. Huge concentration of mass in the middle of these. If you go so far back, there will be lots of intermediate mass. So it'll be almost impossible to go far back in time without examples of gravitational lensing. But this is, okay, it's obviously visually spectacular, but it is also scientifically a very important image. And then if we could just go and have a look at the description of it, it shows a galaxy cluster 4.6 billion years ago, about the same as our sun. NIRCam brought the distant galaxies into sharp focus, tiny faint structures that have never been seen before because of the resolution. Other features include the prominent arcs in the field. This is gravitational lensing, which I referred to previously, but it's very, very obvious in this image. And then the mid-infrared range offers a kaleidoscope of colors and highlights where the dust is, which dust is a major ingredient of star formation. So then it also refers to the spectra, which were determined by the spectrograph is, I think Peter will agree, is probably the most important data that one gets from a telescope, and specifically the James Webb Telescope. And here they're referring to observed 48 individual galaxies at the same time, even though the shutters can theoretically observe 100 of them simultaneously. But that, of course, I did refer to that earlier, implies you get so much more information in a limited time. Right, let's go back to the previous one. Any other comments about this image that you want to add?
Could I just ask one question?
Of course. It's a discussion.
When they refer to dust, is it hydrogen? Is it helium? What is the dust?
Dust is very small particles. I think Peter, I'm going to ask for help from you. It's mainly hydrogen, but you could also find primitive atoms or molecules, which are very small particles. At a later image, one of the images illustrates the important contribution that supernova explosions make to providing gas for the next generations of stars, providing dust from which the next generation of stars can be created. And in fact, that's where all the heavy elements come from. So
it's a mixture of stuff.
Yeah, the dust refers to all kinds of compositions like molecules, and the majority of dust consists of hydrogen and also ionized hydrogen. They call it the H2 regions from which galaxies can start forming. So it is almost like a screening factor to look through, almost like a misty, but very thin and the density is not very high. So, but optically you cannot look through it. It consists basically of all kinds of molecules, but predominantly hydrogen, helium, and also ionized hydrogen.
Thanks, Peter. So in other words, the atomic scale objects, but lots of them. Very
Can
small.
can I ask a technical question?
Of course.
With astrophotography, we take multiple images so that if there's say one image with a satellite or something moving in front of the image, so that we can throw out that one image. So this telescope, do they also make use of multiple images with a stacking process, or do they run a long exposure to get the light in?
I'm not quite sure. I'm assuming that they will take multiple images, but there were examples where they took this deep field, would be, I would assume, as long as possible. And that's why the pointing mechanism of the instrument is. But I do think they take as long images as possible. But I would also assume that they do stack a multitude of them. Is that correct, Peter?
Yes, Dave, the majority of these images are stacked photos that they've taken, and then it's been done with different filters so they can see different aspects of a particular region in sky. And sometimes they also combine Hubble with James Webb to see the composed image of these two or of all the images put together and stacked on top of each other. Then they can even identify more detail into because then the wavelength range is much larger for a particular region. And so the majority of these images, in short, are stacked images.
Thanks, Peter.
Thanks.
Peter, I hope that answers your technical question completely.
The
Pierre?
purpose of stacking for terrestrial astrophotography is really to deal with the movement of the image at the sensor due to the atmosphere having different densities and having turbulence. So we see the star move around a little bit, and that then blurs it. But the whole image is generally affected in this way. So by taking lots of short exposures, you can then re-register it and then get a better detail. The business of layering in order to bring out features from different wavelengths, of course, is an entirely different purpose.
Yeah, I think if we do have time, we can have a look at the website, at the MAST website, and maybe a list of images. They show all the details of the images. I think that they take one image in one filter, in one wavelength, with one filter. They do have different wavelengths with different filters, and then put them together. They might, as Pierre said, have 4 or 5 or 6. And where I've taken all the data from that to make an image, I allocate sometimes two wavelengths to one color, and stack those together, and then I end up with 3 red, green, and blue images, which I then combine afterwards. But obviously you're far away from Earth, so you won't have satellites as a problem, and you won't have atmosphere as a problem, as Chris said.
Okay.
Pierre, I have a question, please. Maybe not sure if it's a logical question, but if James Webb can look so far back in time, would it be possible to say this is what an object or a system developed, what it looked like in ages past, and to track its development through its evolution, as it were? So you could see it 14 billion years ago, and you could see the same objects at a younger date. Can James Webb do that?
One of the objectives is to see the development of galaxies, compare the ancient galaxies with images of the galaxies that we see closer to Earth. But the other one is also to try and study the formation and the development of stars, not by taking different images at different times, which we just on the cosmic timescale, we just won't live long enough. But I think what they are trying to do in some of the images is to take lots of photographs of star formation at different stages, and then looking at them at star formation images of different stars, different stages. It gives an indication, or an experimental indication, of how the stars evolve. And then that, of course, is used as input for modeling, because modeling of astronomical processes is very, very important. So in other words, take a lot of photos of a lot of different stars at different stages of the evolution to serve as calibration data for theoretical modeling.
Okay, all right. I think I've got that. Thank you, Pierre.
Right, can we move on to the next one? One of the science objectives was also to study exoplanets, and this was also one of the first images released and was proof of hydrogen in the atmosphere of an exoplanet. And look at the detail. It's interesting that the wavelength is from 0.75 to 2.75 microns. So we're looking at the molecular spectra of hydrogen, not atomic. But the resolution is very, very clear from this. And there's the description of this image. It's a lot to go through. The extraordinary detailed spectrum, I'm just drawing your attention to this at the bottom, is made by simultaneously analyzing 280 individual spectra captured over the observation. So it provides an hint of the versatility of the instrument. And over the coming years, researchers will use spectroscopy to analyze the surfaces and atmospheres of several dozen exoplanets. From small, there's one image showing that a rocky planet has got little or no atmosphere. Any comments or questions regarding this before we move on to the next image? Okay. Now this is, I think, one of the most recent releases by NASA, and this has got a wealth of information. In fact, those of you that listened to Sterre and Planeta on Sunday evening, Marty Hoffman referred to this particular image, which shows star formation to very, very early stages. The item there is the star itself at the center of the spikes, and it appears as that you must read what the colors actually, the orange-white splash. So that is where the star itself is. It's very young, only a few thousand years old. Now that is really young, because that takes millions of years to fully form. If we look at the description, there's an immense amount of information. First says where you can look for it, at the center over there. Most striking details are the two-sided lobes that fan out from the actively forming central stars, represented in fiery orange. So there's the star, and fiery orange, I would assume, are these ones. When material from more recent ejections run into older material, it changes the shape. The activity is like a large fountain being turned on and off in rapid but random succession, leading to billowing patterns in the pool below. The star's more recent ejections appear in thread-like blue. They run just below the red horizontal diffraction spike at 2 o'clock. Red thread-like blue. There's the horizontal diffraction spike, thread-like blue. I would assume would be that bit over there. This illustrates the point that you cannot, by just looking at the image, say what you must read the description of the image itself. Now turn your eye to the second most prominent feature, the effervescent blue cloud. This is the region of dense dust and gas known both as a nebula and more formula as a Bok globule. Now, Bok globules, when viewed in mainly visible light, appear almost completely black. So this shows you the dust penetrating capabilities of the James Webb. The nebula is important. I just want to see what its color is. The effervescent blue cloud. I'm not sure whether it's referring to this whole blue area or just smaller areas of it. Just have a look at the description again. Sort of reading. The nebulous edges appear in soft orange outline. Let's go back, see if we can see that. Soft orange
Oh, there you go.
outline.
Yeah, that's the edge down there.
Yeah,
That's-
so this is big.
It's right at the bottom. You see that edge
Yeah.
of the region.
Yeah,
That's
that
what the-
is that you're pointing to now. And then that blue, sort of that almost a quarter of the whole image.
Yeah. Okay. There are two other areas to look to compare. Upward is a blobby, almost sponge-shaped ejecta that appears separate. Only a few threads of semi-transparent wisps point towards the larger lobe. That probably were ejected earlier, at earlier stage. So if we go back to the image, I think he's referring to this, or might even be that. But I think this example illustrates two things: how much information is contained in there, and this is also a very recent image. So I think NASA has evolved from providing, let's call it, visually spectacular images to scientifically more detailed description of what they are seeing. But this example clearly illustrates that you must read the notes attached to the images. Any further comments about this particular image?
I can just add something, that the stars in the middle are actually a binary star that's basically being formed. It's not a single star. And the jets that are to the left and right are actually reminding us of, it's a very characteristic effect of star formation. They're shedding some material. After absorption of material, they spread out these jets in the process of star formation. So that is a characteristic feature of young stars that are being formed, to see these jets, and that cannot be observed. If you look at the previous picture of Hubble that also took an image of that region, you only see a black area with no detail in between, and that adds to what Pierre has just said, the capabilities of James Webb to see through the dust in the interplanetary region or in the galactic space.
Thank you, Peter.
That also raises a question: is James Webb targeting areas that Hubble vaguely spotted but didn't understand or couldn't read properly? So now, because how was that image found, or that system found accidentally, or did they home in on it from previous knowledge from Hubble, for example?
I would assume they used previous images from Hubble and information that they gained, and then explore that and see what James Webb can add to the knowledge that they already have. So that complements each other. So I don't think they just zoom in a random direction and see what is in the target that they can see. They use previous knowledge to do a more intelligent and a detailed, calculated observation of a certain region.
Thank
It
you.
certainly shows how much more James Webb can show. It's amazing, isn't it?
I also think there's another component, and that is that, like Hubble, astronomers can submit proposed projects or proposed observations to the science team of the James Webb, and the evaluation committee will judge these against the degree to which it coincides with the prime objectives, the science objectives of the James Webb Telescope itself. So to a certain extent, obviously, if they're looking at something, the chances that Hubble has already observed it is very high. So I think it's not just a case of revisiting Hubble's objectives. These are proposals which come from astronomers worldwide, but they given priority according to the degree with which they meet the science objectives of JWST. Is that correct, Peter?
Yes, that is how it normally works. You put in a project proposal and they can see what is the merit of it and how it complies with their objectives that they want to achieve. And if that incorporates a previous visit by Hubble, then so better, then it can actually add to the strength of the project proposal and also the time that has been allocated on the telescope to a certain project. So it's not just every free for all. It's a highly competitive environment where groups submit proposals and then it's evaluated, and then eventually you are granted a certain amount of time and to observe what you have envisaged to achieve.
I can imagine that that timetable for the next 5 years is already very, very full.
Yeah.
I think that's a fair assumption.
Yeah, could I just make a comment on a previous discussion? I
Yes.
was quite intrigued by Elaine's question about the cosmic dust, so I went and Googled it just now. And actually, the answers that came back, I can quickly read to you. In low-density diffuse regions of interstellar space, the dust is composed primarily of amorphous anhydrous silicates, such as olivine and pyroxene, and of carbon in various forms. Amorphous or partially graphitized carbon, aliphatic or aromatic hydrocarbons, and possibly kerogen-like organic refractory matter. So quite a lot of sort of highly, much heavier. Another answer said simply, dust is made of various elements, carbon, oxygen, iron, and other atoms heavier than hydrogen and helium. So it's actually something I'd never really thought to ask myself. So, and there's another little article here on Herschel helped solve mystery of cosmic dust origins, which I haven't read the article yet. So it's actually quite a very good question that was asked.
Kudos to you, Elaine. Thank you. Thanks, Derek, for the response.
Okay, thank you. Can I just ask another question? Now, if I understand Peter correctly, he said that was the formation of a double star. Is that right? And if so, how can one tell this from the picture or the image, or do you have to read below to see how, how does one know it's a double star?
The object known as Herbig-Haro 4647 has been known for a long time. It's been observed in visible light for many, and analyzing information about it before, it is known to be a double star forming in close proximity to each other.
Thank you.
Right. This is also a fairly recent one. Now, I've got a problem with pronunciation. Fire, what is the correct pronunciation of that?
I call it Ophiuchi. I don't know if that's right.
Sorry?
Ophiuchi.
Ophiuchi. Okay, thanks, Terry. In any case, it's a fantastic image. Once again, visibly spectacular. But if you go and read the detail, it shows a region containing approximately 50 young stars. And this is very close to Earth. It's 390 light years away now. I actually was under the impression that the Orion Nebula was the closest star-forming area to Earth. And here it's now 390 light years away, so it's a lot closer. They're all sun-like stars. Bipolar jets of molecular hydrogen represented in red dominate the image, appearing horizontally across the upper third and vertically on the right. let's just go back to the previous. Oh yes, there we are. These jets, which Peter was referring to as well earlier. Allows us, what's important, and this I think latches onto the question that Peter asked earlier. Webb's image allows us to witness a brief period in the stellar life cycle with new clarity. So it's very short, it's a brief period in its evolution. And if you observe lots of stars like this, then it gives you information about how they actually evolve. Any more comments or questions about this? Right, let's move on and see if we can get some. The most distant active supermassive black hole to date. Now, I think this is quite interesting. It existed just 570 million years after the Big Bang, which is very, very shortly after. And then there's a whole discussion about the mass of it. It's regarded as surprisingly small, but it also raises the question of how could such supermassive holes form so shortly after the Big Bang? Because my perception is that you've got massive stars forming, basically mainly hydrogen, a little bit of helium, and then they formed galaxies, and then in the galaxies the black holes formed naturally. But this is 570 years after the Big Bang, so that's very, very short. And there's a whole big discussion about this. I'm not quite sure if I must say more about that. I think there's been a lot of discussion about the surprising age of the first black holes or supermassive black holes. And I think this is illustrative of exactly what's happening. Webb is using new technology, and the results that it sends back to Earth, in some cases, has not been anticipated. So it's got to be interpreted from anew by astronomers, and I think that's what makes it such a groundbreaking and exciting project. For example, this is now one of its key scientific objectives, looking at the very early universe and how galaxies and supermassive black holes evolved so early. Any other comments regarding this?
Perhaps just a comment on that. The age of the universe thing, there's been for quite a while a bit of controversy about this with the James Webb findings. There was recently a group that theorized that the universe could be twice as old as we thought it was, not 13 but 26. And I have looked at YouTube videos by quite a few of the sort of creditable astrophysicists, and they've got very good reasons, several reasons why that is just totally incorrect. It's not true at all. So yeah, it's more or less, maybe it needs to be tweaked a little bit, and some of the physics needs to be tweaked, and there must be some new physics to explain some of the findings, but the general sort of 99% of the theory is basically intact. The standard lambda CDM theory.
Yeah. Sorry, can I ask another question? Yeah, I'm sorry, maybe I should know these things, but I don't. Two questions. Could you point to a black hole on that picture? And then secondly, how do they find these black holes? It's just because of the gravitational area around it that they surmise that if they can't see anything but that everything around it is behaving in a way suggesting a gravitational pull. Is that the way they see them?
I'm going to speculate, but trying to do so reasonably intelligently. You cannot see a black hole, obviously, but you can see its gravitational effect on its surroundings. And amongst others, Peter referred to the jets that you typically get from star formation. You get even stronger and more energetic jets on two sides, opposite sides of a black hole. As it sucks in material from outside, it forms a disk around it, and along its central axis, you get very high energy radiation being emitted. So I would assume in the case of James Webb, those jets will have very high energies, and you will also see the inflowing gas will also emit radiation. And by determining the speed of rotation, etc., there will be telltale signals which a sophisticated instrument like James Webb will detect. But it's not you can't see it yourself, and I don't think one can actually see from the timescales the effect of stars near it. But you do see the radiation that is from the disk surrounding it and from the jets. Peter, can you answer more specifically?
No, I think you've already answered it. The only way to detect a black hole is the indirect evidence of the environment around it. Like, for instance, the Sagittarius A black hole in the middle of the Milky Way has been detected by looking at the radiation around it from incoming gases that are being accelerated through the gravitational field of the black hole, and then you can really detect it, but you cannot see the black hole itself. You can only see the event horizon around it of interacting gases that's coming and streaming into the black hole itself.
Thanks, Peter. Any other comments?
Okay. No, I was just thinking there might be evidence of one detected in that picture there, in that image that we're looking at.
I doubt that there will be visible evidence on an image like this.
Okay.
Okay, then just a very quick one. James Webb detects dust reservoirs in two supernovae. It observes, I think I've mentioned previously, that these are type 2 supernovae, in other words, massive stars, which eventually collapse directly into a black hole. And they throw off the outer shells a lot of dust getting back to that. And that seeds the universe with elements heavier than hydrogen and helium. It's a very, very important part of it. In fact, all elements heavier than silicon in our bodies as well have been recycled through supernova explosion in the past. But this is just interesting that, first of all, James Webb could observe the dust formation, and secondly, that it could actually determine the mass of the dust ejected from these supernova. I think there's a lot of information there, but I think that's the essence of what the image and the notes actually say. Can I move on to the next one?
Yeah.
And this is very similar to the previous one, but I think there's a new angle to this, and that is that before, in the first billion years after the Big Bang, we had galaxies that actually made the area around them. The universe was then opaque, but they made radiation, made the area around these galaxies transparent, and it's almost like bubbles growing, which the next image shows you. In this illustration, the star forms and galaxies assemble, and then it begins to change the gas around them, making it transparent, and they grow almost like bubbles in a kettle boiling, and then you eventually have the clear universe at the end of reionization. So once again, interesting that James Webb could actually observe this in confirmation with what is expected. Any other comments regarding this?
I think that's quite stunning, actually.
Sorry?
I think that whole, bubble formation, I mean, it's all been theory up until now.
Yeah, it's well,
Really quite stunning to see that.
it also says they used Webb to precisely measure the gas around the galaxies. Ionized gas, 2 million light-year radius around the tiny galaxies. And they grow larger. This is quite spectacular. Okay, and then once again, going back to the early universe, it's observing the formation of a new huge galaxy cluster. If you go to the notes, it describes it in greater detail. These are 7 different galaxies forming simultaneously at a redshift of 7.9, 650 million years after the Big Bang, grow in size to resemble the Coma cluster. So I think I don't want to add much more to this. There is a lot of information in these descriptions, and you can go read them all, look at the image and read the explanatory notes on the NASA website. Any further comment regarding this? Okay, then another spectacular image. It's a merger of 2 elliptical galaxies and lots of radiation in the infrared, so that's why James Webb could see it. And as it sums it up, a stunning smash-up of 2 spiral galaxies called OP 220. Previous radio telescope observations revealed 100 supernova remnants in the area of less than 500. Hubble Space Telescope uncovered the cause of the parent galaxies. Each of the causes are stating the outskirts of this merger. James Webb reveals that tidal tails of material blown off by galaxies by gravity is represented in blue, evidence of the galactic dance that is occurring. Organic material represents in reddish orange, appears in streams and filaments across the image. Once again, looking at the image, there's no way that you'll be able to decipher what you're looking at if you don't read the explanatory notes with it. Then just a very quick one, getting back to exoplanets. James Webb used to calculate the amount of heat energy coming from the rocky exoplanet TRAPPIST-1c. The results suggest that the planet's atmosphere, if it exists, is extremely thin. So it just illustrates the power to observe and analyze exoplanets, which is one of its prime science objectives. And then I think the second from final, star formation in dusty ribbons in metal poor. It's NGC 346 in the Small Magellanic Cloud. Now, what's interesting there is that the Small Magellanic Cloud is very old, so it's very poor in elements, in metals, heavy metals, or elements heavier than hydrogen and helium. So it was thought that there would be little dust, but Hubble Webb proved the opposite. And if we look at the description, it's about 200,000 light years away. Many more building blocks. There are 2 different colors. The pink gas represents energized hydrogen, which is about 10,000 Celsius. You can't get star formation at such high temperatures, while the more orange gas represents dense molecular hydrogen, much colder, around minus 200 Celsius, and associated dust. And the colder gas obviously provides an excellent environment for stars to form. And here's an example of what I said, using different filters. In this image, blue was assigned to the wavelength of 2 microns, the shortest wavelength. Green was assigned to 2.77, orange to 3.35, and red to 4.444. So there are 4 channels. Derek, you referred to assigning to 3 channels of a normal RGB image processing. There are 4, and I saw one other image which I couldn't find this afternoon, which used 6 different filters. But I think this is another stunning example of the power of James Webb. Any comments regarding this? Right, then, which is becoming increasingly powerful, is multi-wavelength images, where you combine images from Hubble in visible and James Webb in infrared, Chandra's X-ray, and even gamma rays with XMM Newton. And each of the different, they're normally represented in different colors. They each represent different energy levels or temperatures of the different processes. And this was discussed quite, I think, very tellingly by our previous guest speaker, who spoke about the violent universe. And then the last image that I have just referred to, which I find very interesting, and it illustrates the focus of James Webb studying the very early universe. It's strands of the cosmic web, which all these circles illustrate the strand. Strands of 3 million light years long filaments. These existed just 830 million years after the Big Bang. I think that concludes. Any comments, any questions about this? I think it's very clear from the sample images that I used that James Webb is very diligently pursuing the prime science objectives of the project as a whole. And it's been an unqualified success. In the past, I've used the term that Hubble is the single instrument that has contributed most to mankind's understanding of the universe's origin and its evolution. And I think it still stands, but James Webb is extending the horizons and adding much more detail to the overall picture. More about early black supermassive black holes. And I think that's all for now. So if there's any questions, I will refer them to Peter.
Yeah.
And if there's time, then maybe Derek can show a few more images from the website. But thank you for all your contributions to this discussion, and particularly for the knowledgeable contributions from a number of you. The intention was a discussion, not a talk, and I think we've succeeded in that. So thank you for all your contributions.
Thank
Yeah, I have a
Thank
couple
you
of
very
comments I can
your
add.
expert presentation. I know you don't want to call it a presentation, but it was your expertise that made it so valuable. Any more questions?
I have a couple of comments I can contribute.
Go ahead, Chris.
So, firstly, keeping the instrument cold is vital because it's operating in a very long wavelength part of the spectrum. And the sun, of course, presents a problem in this respect, even though it's relatively far away. I mean, here at Earth, we're getting a kilowatt per square meter of solar isolation, and this is not that much farther away. So the shields are therefore the absolutely vital component. And if you just take, say, a piece of cardboard and you hold it to shield the sun, then the heat will flow from the hot side to the cold side, and after a while, the whole thing is going to be hot, and you will be able to measure a fair amount of heat on the cold side. So clearly, making a barrier isn't just a question of putting something in the way and expecting it to block the sun's rays altogether. And so I found it quite difficult to understand, you know, how a thin mylar sheet could actually perform as an effective barrier to the solar radiation. So the answer to this is actually very ingenious. On the cold side of the surface, the heat radiates out in all directions. So there's like a 180-degree solid angle fan of radiation coming out. Even if you have, say, a laser that's absolutely straight shining on the hot side, all right, the heat is going to radiate out in a fan. And that is the key to the success of the solar shield here. So what they've got is 5 layers of aluminized mylar. So the sun's rays will arrive and mostly be reflected, but still with a portion absorbed by the first layer. That then, instead of having like a 1/2 degree angle like the sun's rays come in at, this will fan out over at about 180 degrees total. And that means that when it hits the next layer, it doesn't hit it normal, straight, you know, at 90 degrees to the surface. It hits it at an angle, and that allows it to reflect it sideways. And so it will bounce between the 2 layers, and from this process, it gradually becomes more shining out at 90 degrees than in the line of the approaching sunlight. And then each layer, of course, successively will still absorb some of the energy, but by the 5th layer, there's practically none left. I thought this was intensely ingenious.
That is definitely so. I wasn't aware of it.
Chris, just a question: is there any actual cooling? I seem to remember they had a long time period when they were getting it cooled down to temperature. Was that just from hanging around there, or is there an actual some kind of a compressor taking heat away from one side to another side or something like that?
Yeah, look, firstly, they obviously want to keep the whole telescope as close to the conditions in which it's supposed to operate. And so that they would have had, you know, sort of active external cooling to look after it while it was on Earth. But I think some of the instruments will be cooled with like Peltier cells where, you know, it's an electrically operated system that basically siphons off the energy. So, but I haven't investigated that, but it's almost, you know, a certainty that they will do that, because the amount of noise in the system is related to the temperature of the system. So the lower the temperature, the lower the intrinsic noise, and therefore the smaller the signal that you can actually detect. So there will definitely be active cooling, but it won't be like a mechanical system. It will be electrical.
Sorry, Sharon.
The other thing is that this is probably the riskiest project ever to fly into space. When you're looking at the project risk, you look at single points of failure. So the single point of failure is if this goes wrong, it's going to jeopardize the entire mission. And mostly you would limit it to maybe 5 single points of failure in the system, and then you can have sufficient mitigating mechanisms to control that. This is something like 580 single points of failure that could potentially have prevented it from operating once it was launched.
That's quite incredible. All right, can I share the images that I processed myself?
Sure.
Mm.
Okay, so this one, remember the one that Pierre showed up? So this is the one that I took the data and made my own one. If you look at the one that the James Webb guys showed, this area was like more blue. This sort of wispy stuff here, I've got it as red, where they had that as blue, and they had very dark shadows here. I wanted to bring out more detail here. So mine looks,
Where is it?
and then also if you look at the resolution, I show a lot more detail in this, the way I process it.
Derek, I'm not
this-
seeing your image.
Oh, sorry, just let me try again.
Yeah.
I said, let me just, oh, I didn't click the final button there. Okay, can you see it now?
Yeah.
Okay, sorry. I didn't click there was, you've got to do things 3 times before it goes through. So this is the one I produced, where you see this area, the James Webb, or the one that the guys, their scientists gave out to the public. They had this more of a blue there, where I've got that more of a red. And then this they've got very dark areas here where I've brought out more of the detail there. And I show, a lot sharper detail as well. I actually, just using Topaz denoise, it brings out a lot more detail than their processors did. And then the other one I've got is Stefan's quintet. Just let me, sorry, can you see this one?
Yes, we can.
Can you see Stefan's quintet now? Okay. So again, same thing. I've got slightly sort of more enhanced colors, brighter colors, slightly different colors, sharper detail. So yeah, these are 2 of the ones that I did. I actually had a look at some of the latest images on the MAST website. But that data is locked for public. It's not available for public use until sort of March, May next year. Yeah. Okay. At some stage, if anybody's interested in how that processing gets done, I can do a presentation on that. All right. Thanks very much, Pierre. That was very good.
Yeah. Derek, can I just ask you a question?
Yeah.
Yeah. When you did those images, now then you said you had different colors. So did you select different colors for the different wavelengths that were different to theirs?
I think I downloaded, if I can find the file. Anyway, I think it was about 5. It was about a gigabyte in each wavelength of data. So I was working with a single image, which was about 5 gigabytes big. So it was rather rough on my computer's processor, and it took quite a while to get it done. But then I think there were 5, and I took, say, 2 wavelengths close to each other and allocated those to a color. I would combine the data of those 2 into one image, and allocated one color, so that I got, out of the 5 filters, I then got 3 color images, and then just did the process as normal in my processing software. Johan, did you have a question?
Thank you. That's most
Just to say that I'm impressed with what you've achieved.
Nearly as good as the images taken with your telescope, Johan.
Well, there you go.
Elaine, did you have another comment on that? Sorry.
No, I just wanted to say thank you. I'm very impressed with all of you.
Okay. I think there's a huge amount of stuff, that has been sort of analyzed and found that to take us, to take the scientists a lot of work to pull out all the information, but there's an enormous amount. It's quite exciting times, and I think it's only going to get more exciting as time goes on with the James Webb sort of findings and stuff. I'm looking very forward to Peter's presentation. Peter, are you still here?
Yes, I'm still here. No, I'm working on it, and I'll present a little bit more of our own solar system stuff as well. So it will complement what Pierre has said tonight, and hopefully it will be of interest to the whole greater community.
Great. And tell me, just remind me the time. Is it 10 o'clock? I think Pierre said.
It's 10 o'clock, the Friday morning of the 1st of September in the Catholic Hall.
Okay.
Peter, I must just speak, that will be a presentation. Tonight was
Yes.
to be a
Yeah.
discussion.
I'm sure there will be a discussion afterwards, but it will mostly be a similar presentation that you normally deliver to the astronomy community.
Yeah, I think Peter must request the HRC to turn up in force there. I think it's worthwhile.
I'll definitely try and book my seat.
Peter, could you just send me, please, the details that I can send on to membership?
I'll do that as I've got everything in place, and then I will send you a copy of what you can distribute to the whole community.
Thanks very much. Okay.
Peter or Pierre, just remind me for people that aren't members of U3A, what is the entrance fee for visitors?
I don't know, because I'm not a member of UTA myself, so I will just pitch up. But I think there might be a small fee payable at the door, but
Probably
I think you can from possible.
I know it
10 or
was
20
30 rand up on stage, but I think that's probably gone up by now, some years ago.
I think it's about 25 rand if you're a non-member.
So maybe we must just, before we send out the email, just check on that with Gert or somebody else.
Okay.
Just so people know. Great, thanks very much. Any more questions?
Hi, may I ask something?
Go ahead.
Are you aware of the profile of the U3A, the people, the attendees? Are they like scientists? These are people who have a general curiosity in life. They're probably all retired. Do they all have a scientific base or an interest in science? I'm asking this, for instance, to appreciate the spectrum of wavelength to frequency, and then what the visible portion is, what the spectrographs look at, and what the scopes listen to, the radio scopes, that one can get that in the perspective. And then also, how does one know what is helium in space, and what do you know where hydrogen is and how much iron there is? That gets done by analysis of the wave responses that you see or that you receive. So something along that line, I think as a layman, I would appreciate if I were part of the U3A audience.
Would you like an answer on that now? I think Pierre can sort of answer you now on that.
No, it's an open question to ask before presenting to that audience of the U3A.
I'm aiming my presentation at the general public, not at an astronomy group. So the main emphasis will be on a general understanding of what's happening in the universe as seen by the James Webb Telescope. So it won't be too technical, but I cannot cover all wavelengths from astronomy, from the radio to the visible. That is impossible to do. I can only concentrate on what James Webb is doing, and that is in the infrared. So otherwise, I will have to talk for a whole week on end to get a presentation. So, but don't be afraid, it won't be technical, and it won't be leveled at the university professor's level.
Appreciate the response. Thank you.
All right. Thanks everybody for your attendance and for asking intriguing questions and so on. Thanks for a superb well, I have to call it a presentation. I don't know. Thanks for giving us a superb discussion, Pierre. And any more questions? Fine, going on before we log off.
Thanks, everyone. Good night.
Thanks, bye
Good
all.
night, everyone. Thank you very much.
Thanks, and I'll send the
A
recording link.
huge thank you.
I'll send the recording link to Peter if anybody wants it. Okay.
Thank you, Derek, Pierre,